Hi there, folks. Today we're looking at mutually exclusive and inclusive events. And really, these are a continuation of our compound events that we've been talking about. Events, remember, are two or more events linked by the words and or the words or. When we talk about mutually exclusive and inclusive events, we're talking about those or probabilities. All right. So, or probabilities are when we're talking about mutually exclusive and inclusive. All right. So mutually exclusive events are events that cannot occur simultaneously. In other words, there's no overlap. All right, between those two things. All right. So examples that if I had like blue marbles and red marbles, all right, and there were no other marbles that I had, they would be mutually exclusive if I was looking at the probability of a blue or a red marble, because there's no marbles that are blue and red at the same time. Okay, there's no marbles that are a mix of those two. All right, it's either blue or it's either red. They are separated, they are distinct. That's what mutually exclusive means. Okay, they are separate. All right. For or probabilities of mutually exclusive events, pretty simple here. If I have the probability of A or B, all right, there's that word or, we just do the probability of A plus the probability of B. So or, we add the probabilities. And if you recall, when we did and probabilities, and we multiplied the probabilities. So and we multiply, or we add the probabilities, okay? For example, it says one card is drawn from a standard deck of cards. So like playing cards, those kind of things, all right? What is the probability of drawing a 2 or an ace? All right. And if you don't have any knowledge of a standard deck of cards, that is okay. I will give you that information as you need it. For example, like the standard deck of cards, there are 52 cards in a standard deck of cards. All right. If you're looking at how many twos are in a standard deck, there are 4 twos. There's a two of hearts, a two of clubs, a two of spades, and a two of diamonds. All right. Ace, same thing. There's 4 of those as well: hearts, clubs, spades, and diamonds. So now I have all the information I need. And the idea here, these are mutually exclusive, because if you've ever played cards before, you'll know that there are some cards that have twos on them. And there are some cards that have ace that are considered aces that have A's on them. But there are no cards that have twos and that are two and an ace at the same time. There's no cards that have both of those features simultaneously. So these are mutually exclusive. It could be a two, it could be an ace, but it can't be both. All right. And so these are mutually exclusive. So if I want the probability of one thing or the other, I say, okay, what's the probability of 2? Well, there's 4 of those out of 52 cards. What's the probability of an ace? Well, there's 4 of those out of 52 cards. And or tells me I should add these. And lucky for me, when I look at this, remember, when you add fractions, you need to have common denominators. Well, you should automatically have common denominators right out of the gate. So make sure you add these before you do any simplifying, okay? Don't mess up your common denominators. I already have a common denominator, so I add the numerators. Denominator stays the same. And now let's reduce that fraction. They're each divisible by 4, so that's a 2 over 13. And yeah, make sure you reduce the fraction at the end. But that's it. Or we take each probability and we add them, okay? Here, a bag contains 4 green, 6 yellow, and 8 blue marbles. One is drawn at random. So what's the probability of a blue or a green? And again, these are mutually exclusive because I clearly have blue marbles. It states that. I have green marbles. It states that. But I don't have any marbles that are a mix between the two, that are kind of a swirl pattern between blue and green. There's no overlap. It could be one thing, it could be the other thing, but it can't be both. All right. So blue marbles, the probability of a blue marble, there's 8 of those out of a total of, looks like 18. Or means we add, so I'm going to put my addition sign. The probability of a green marble is 4 out of the 18. Okay, and once again, I already have common denominators. Don't mess them up. Add the numerators, denominator stays the same. And now let's reduce that fraction. They're each divisible by 6, so that's a 2 out of 3. Okay, so the probability of blue or green is 2/3. This one, yellow or green, so the probability of a yellow marble would be 6 out of the 18. Or means we add, the probability of a green marble is 4 out of 18. And now when I add these up, I already have common denominators. That's 10 out of 18. And now I can reduce the fraction. That's a 5 out of 9. Again, or means we add. So we come up with each of those probabilities, and then I add them up. Down here, the probability of a purple or a blue. So there are no purple marbles, so it's 0 out of 18, and that's okay. Or means we add, the probability of a blue marble would be 8 out of 18. And now I add them up, that's 8 over 18, which reduces to 4 over 9. Okay, and this is a kind of a neat example because the probability of purple being 0 because there are no purples. Keep in mind what or means. Or means one or the other. So if I said the probability of purple or blue, either getting a purple or getting a blue, well, since there are no purples, my only option is to get the blue, which is why the probability ends up being 8 out of 18, just for the blues, essentially, okay? Because it's one or the other, so the blues satisfy that condition, okay? So now let's talk about inclusive events. This is where it becomes a little bit trickier, okay? So inclusive events, sometimes known as overlapping events, all right? It depends on the textbook that you're using, but if you want to make a note to self, sometimes we call these overlapping. Overlapping events, so basically, if the events have overlap. In other words, if the two pieces kind of have something in common, what ends up happening is if I count them separately, I end up counting certain things twice. All right. And that's kind of what I'm trying to avoid here. All right. Sorry, I just realized I spelled overlapping wrong. I think there's two P's in that. But again, if there's overlap, in other words, the two pieces of this thing have something in common, we have to basically subtract that thing because we're going to accidentally count it twice. So as you look down here, so or probabilities of inclusive events, probability of A or B, it's the probability of A plus the probability of B minus the probability of A and B. All right. And the reason we're doing that is because if there's overlap, all right, so if I said, students in my classroom who are wearing students in my classroom who are wearing red shirts, or students in my classroom who are wearing glasses, all right, there could be some overlap there. There might be somebody wearing glasses and a red shirt. And if I counted up everybody who is wearing red shirts, I would count the kid with glasses and a red shirt. But then separately, if I counted up all the people with glasses, I would once again count that same kid with glasses and a red shirt. So I would count that kid twice. I have to subtract them because essentially I've counted them twice by accident, okay? For example, I'm going to go back to the cards for a moment. One card is drawn from a standard deck of cards. Once again, there are 52 cards in a deck. What's the probability of drawing a queen or a diamond? So queens, there's 4 of those in the deck. Diamonds, there are 13 of those in the deck. Okay, so there's a diamond for each type of card. So there's an ace of diamonds, a 2 of diamonds, a 3 of diamonds, a 4 of diamonds, all the way up to, jack, queen, king, ace. Okay, so this is kind of the situation. The thing is, there's overlap here because if you think about the queens, there are 4 queens in the deck. There's a queen of clubs, a queen of hearts, a queen of spades, and a queen of diamonds. All right. And then when you look at all the diamonds in our deck, well, if I counted up the diamonds, I would count the queen of diamonds again. So essentially, I'm counting that one twice. All right. And so if I kind of think of this, let me show this to you in a Venn diagram first. Again, you won't have to do this every time, but just to illustrate why we're subtracting this thing, if we were to kind of look at all the cards in the deck and say, okay, there's the queens, there's the diamonds. Okay, so this is the diamonds, this is the queens. If I started looking at the queens, I would have the queen of hearts. I'm such an artist, right? The queen of spades. Spade looks kind of like an upside down heart. The queen of clubs, which kind of looks like a 3-leaf clover. And then the queen of diamonds, see, that's in the overlap. It's a queen and a diamond at the same time. And then if I counted up all the diamonds, I would have the 2 of diamonds, the 3, the 4, the 5, the 6, the 7, the 8, the 9, the 10, the jack, the queen, which is already listed in the middle here, the king, and the ace. All right. And so if I started counting all this up from a Venn diagram perspective, well, just count them. Let's see what happens. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that would be 16 out of the 52, which then reduces. I won't reduce it here because I'm about to do this problem kind of the more mathematical way. But if I kind of approached this the same way I did before, I would say, okay, queens, there's 4 out of 52. Or means we add diamonds, there's 13 out of 52. And see, if I were to add these up right now, you see that it would give me 17 out of 52. And we already know it's only supposed to be 16 out of 52. It's because the queen of diamonds got counted twice. See, this 4 includes the queen of diamonds, but this 13 also includes the queen of diamonds. And since there's not 2 of that card, I shouldn't be counting it twice, which is why I then subtract how many queen of diamonds there are, which is 1 out of 52. Okay, I subtract the overlap because I counted it twice. It's like I made a mistake and I'm correcting that mistake, but that's expected to happen. Okay, and now let's reduce this thing to each divisible by 4. That gives me a 4 out of 13. Okay, so these are the ones that are top inclusive events. You have to subtract the overlap. If we look at these guys, a jar contains 5 green cubes, 6 red cubes, 8 green spheres, and 10 red spheres. One object is pulled. What's the probability of red or a cube? And again, these are inclusive because we have objects that are red and cubes at the same time. So if I talk about the red objects and the cubed objects, they're not completely separated. There's overlap between the two, okay? So here I would say, okay, the probability of red, there are, let's see, 6 plus 10, that's 16 red objects out of a total of, hold on, I can't even find what I'm looking at, 29. Or, so that means I add. When I look at the cubes, there are 11 cubes in the bag, or in the jar, 29. But see, what's happened as I counted the red objects, I counted the red cubes, and then as I counted the cubed objects, I also counted the red cubes. So those 6 objects have been counted twice. They got counted as part of the 16, and then they got counted again as part of the 11. So what I have to do is I subtract the overlap, which is the 6 out of 29. It's the 6 of them that I counted twice. So now by subtracting that, I'm only counting them once. All right. And so here, let's see, when I combine all those, it gives me a 21 out of 29. And that's it. Okay, so we just have to remember to subtract the overlap when there is overlap. All right. If I look at this one, the spheres, let's see, there are 18 spheres in this thing out of 29 total. Or means we add green objects. There are 13 green objects. And now what happens is I've counted the green spheres twice. Those 8 green spheres got counted when I did the 18, but then they got counted again when I did the 13. So I have to subtract the 8 out of 29. I have to subtract the overlap. All right, so that gives me a 23 out of 29. And really, if you had added those without subtracting the overlap, hopefully you see that that goes over the value of 29, which is impossible. All right. These guys, let me scoot these up so we can still read the question as we do these. So this one, the cubes, let's see, there are 11 cubes out of 29. Or means we add, once again, the green objects, that is 13 out of 29. But now all the green cubes got counted twice. So there's 5 objects that got counted twice. I have to subtract the overlap. Okay, so really, the math here is not hard. It's identifying whether or not there's overlap, identifying mutually exclusive versus inclusive, just so we know what we have to do. All right. Red or a sphere. In terms of the red objects, once again, there are 16 red objects. Or means we add. In terms of the spheres, there are 18 spheres of the 29. And right away, you can see we're going to go over the total amount. How can there be, you know what I mean, 16 plus 18? There's more than 29. We only have 29 objects. It's because I've counted a bunch twice. I've counted all the red spheres twice, and there's 10 of those. So I have to subtract that so that I'm only counting them once. Okay? And so that gives me a 24 out of 29. So again, mutually exclusive is when there's no overlap. Those are the easy ones. We just add up the probabilities, okay? Those are the good or probabilities, the ones we hope are all over the test. And then the inclusive one is when there is overlap, we still do the same thing. We add the probabilities, but then we subtract the overlap so that we're only counting it once. Okay?